In this video, we're going to be going over a few more algorithms on binary search trees, and I think this will give some nice practice tracing and understanding algorithms on trees. So this is the first one we're going to look at. So this is a mystery function. It is fully described right here, and the question is what value is returned for the tree here that is shown. So the idea here is we're going to trace this code to determine what value is going to be returned if we run the algorithm on the tree here on the right. So we can see that the first thing that happens in the algorithm is that there is a cur pointer that is starting out at the root of the binary search tree. As long as that pointer is not null, we're going to go ahead and move into this loop here. So if it's an empty tree, it's going to stop, and if it's a non-empty tree, it's going to continue on into this while loop. So what does the while loop says? It says while the current pointer's right pointer is not null, go right. So basically it's saying if the current pointer has a right pointer, go to it. So the first check is yes, 22 has a right pointer, and so it's going to go into the loop and it's going to update cur to now point to the 22's right pointer, and then it's going to check again. Does cur's right pointer exist? Yes, it does, so it's going to go ahead and go to it. And then it gets to 61 and it says, does 61 have a right pointer? No, it doesn't. Its right pointer is going to point to null, which is going to make this loop false. So then it's going to go down to this return value, and it's going to return the key associated with where cur currently points, which is 61. So in this case, what does this function do? Well, this function is a maximum function, so it's able to determine the maximum of a binary search tree. It's just interesting to look at how different algorithms are so different depending on how the structure of the data is, right? Because we can be assured that a binary search tree is structured in this way, where if you go left, it's less. If you go right, it's greater. We can easily find the max or the min by just navigating the tree to the right or the left until we've reached a null pointer. Obviously, if we were dealing with data that was unsorted in an array or a vector, this algorithm is going to be more efficient than that, because here we only have to go the height of the tree. There, worst case, we'd have to sort through all the data. However, if we had a sorted array or vector of data, that would obviously be better than this, because we could just go to the first if it was a min, or the last if it was a max, or depending on how it's sorted. So these are the kinds of things that are interesting to think about as you start structuring your data in these different ways. Let's look at another algorithm. So we're going to look at this tree, and the question here is another mystery function, mystery 2. What value is returned for the tree shown? So first we have a mystery function that calls a recursive helper function. So this recursive helper function is receiving the root of the tree here, right? So the root is 14. Once it goes into the recursive function, which is called underscore mystery 2, that means that that parameter passed in initially is the root, so cur is going to point to root. So then when you're into the function, you can see that this is a typical recursive function where you have a base case and then an else. So the base case is if the pointer itself is null, then return 0. Otherwise, do all of this. So obviously we're starting at the root of a non-empty tree, so we are not in the case where our cur is pointing to null pointer. I'm going to trace this function a little bit different, and I think everyone kind of has their own way of tracing recursive functions, but it takes a lot of record keeping to keep track of where you are. So what I'm going to do is I'm going to keep track of what recursive call I'm in by just labeling which node has gone into the function. So right now cur is pointing to 14, so I'm in the recursive call for cur pointing to 14. And then over here, I'm just going to write what's returned from the function to keep track of, where I'm at in this recursive tracing. Recursive tracing is really tricky, and sometimes a debugger can help you trace your code if something is wrong, but I think a lot of people just prefer to trace it by hand so you can really understand what it's doing and that it's doing what you intended. So the return here says that I'm going to return cur's key, so in this case that's going to be 14, and then it's going to return the recursive call to mystery 2 going left and going right. So it's going to go left and then it's going to go right, and it's going to return whatever is returned from those calls. So this is where it's going to start to get complicated. So I'm going to go ahead and go left. So that's the first thing that happens, is that we're going to go left. So if I go left, I'm going to be inside of the recursive call for cur pointing to 7. So I'm going to keep track of where I am there. Cur is not pointing to a null pointer, so again our return is going to be the cur's key plus going left and going right. In this case, at 7, both the left and the right are null, so we know that in both cases we're going to return 0 out of those recursive functions. So here this is pointing to a null and this is pointing to a null. So as we recurse in and out each time here, we're going to get 0. So I've now completely finished a recursive call going to the left, and I pop back out of it, and now I know that here I have 7 coming back out of the cur pointing to 14 call. So I've gone left on 14 and I've finished that, so now I'm going to go right. So when I go right, I'm now going to be pointing to 26, and so I'm going to record keep over here that I'm inside of the 26 call. It's not null, so I first am going to return 26, the cur's key, and then I'm going to go left and I'm going to go right. So my first step is to go left, which means I'm now in another recursive call inside of 20. When I go inside of 20, not pointing to null again, so I'm going to return 20. And then I'm going to go left and right from 20. So going left is null, so I know I'm going to return 0 from that recursive call. And going right is going to require me to now go into the 23. When I go into the 23, I am going to return 23's key, which is 23, and then I'm going to visit both of its left and right, which are both null pointers, right? So both of those will return 0, and I've now completed my exploration into the 23 recursive call. So now I'm going to back out to where it came from. So 23, this came from the call to 20, right? And here I am needing to finish this side of the 20 recursive call, which is going to return 23 here. So now I've finished that, and I'm going to go up to 26. So remember, with 26, I was just going left. So now I've finished it. I've gone through 20, and now I'm coming back up to 26. So I'm going to return where I just was with 20, which is the 20 plus 23. And now I need to explore 26's right. That's my last one. 26's right is a null pointer, so it's going to return 0. Now I've finished 26, right? So I've finished all 3 calls in 26. So now I'm going to go back up to 14 where I came from. And remember that where I am here is I had just gone to 14, I went left, and now I'm just finishing the right. So rights is everything that I did in 26. So that is 26 plus 20 plus 23. So that is the complete recursive tracing for this recursive mystery function. Now, what is it doing? Well, as you might have noticed, this is a sum algorithm for a binary search tree. So what it did is it explored the whole tree, and as it did, it returned each value and everything that was underneath it, and that's how it was able to keep track of the sum. Now, this traversed the tree using a pre-ordered pre-order traversal. So the pre-order traversal is do something, go left, go right. As you all know, since we already covered traversals, there's 3 types of traversals. So you could sum a tree in multiple ways. Pre-order traversal would be do something, go left, right, which is what we're doing here. In-order traversal would go left, do something, go right. And then post-order traversal is go left, go right, and then do something. So this one just happens to be a sum that's in pre-order traversal. And I hope this helps kind of tracing out this recursive call like this and being really explicit and deliberate about it. And maybe you have other ways of keeping track of your tracing that works for you. Maybe this gave you some ideas, or maybe you liked the way that I traced. But either way, you have to figure out some way to keep track of recursive calls. The second thing is that when you're recursively tracing a function, make sure that you think of a tree that is small enough that's reasonable to trace. With the last algorithm that we did here, a larger tree is okay because it's not that complicated to figure out the max and just keep going right. But when you are doing and I never added that up, but 14 plus 7 is 21, plus 26 is 47, plus 20 is 67, plus 23 is 90. So we get 90 here as our sum, which is just the sum of all the elements. But like I was saying, when you're doing recursive algorithms on trees, it really does help when you're tracing to trace on smaller trees, but also non-trivial trees. All right, so that is it for this this video on more algorithms on BSTs. Thanks.